The topic of this screencast is solvation effects and the use of something called the Born self-energy calculation to understand and approximately quantify solvation effects. So earlier on when we talked about the electrostatic force, we spoke about the dielectric constant. Solvation effects of course, involve the interaction. Life is a phenomenon that pretty much exists in water. The dielectric constant we saw earlier was a important factor in attenuating the electrostatic force due to the alignment of the fixed dipoles in water with electric fields and their interaction with electrically charged particles. Solvation is largely an electrostatic phenomenon in terms of the enthalpy component of it. Later on, we'll see that the entropy component of solvation is tremendously important. And towards the end of this section of the course, we will talk extensively about something called entropy-enthalpy compensation. But at the moment, we're going to talk about the enthalpic component of solvation, which again reflects primarily the interaction of the fixed dipoles in water with charged and polarizable solvent species. So we're going to start by doing something called the Born self-energy calculation. This is named after a very prominent physicist named Max Born. He was extremely influential in many areas of physics in the first half of in the early part of the 20th century. He is somewhat notorious in some circles because his granddaughter was someone named Olivia Newton-John. I'm a great fan of pop music, and she, however, is basically a notorious character in the pantheon of pop music. She's the granddaughter of Max Born. Says something rather scary about genetics. In any event, Born did many influential and clever things, and we're going to start today's this screencast with an explanation of something called the Born self-energy calculation that he came up with. So this is an example of what physicists call a Gedanken experiment. Gedanken means thought. So this is something that you really, we're going to now go through again, sort of a theoretical experimental procedure. This is something that would not be easy to do in practice, but the analysis is quite informative, and this is a common tool in theoretical physics, again called the Gedanken or thought experiment. So we're going to start with an atom in radius r, and we're going to assume that to begin with this atom has zero charge. This atom is in a solvent, and so it could be water or it could be any other solvent. What we're going to do as we go forward, we're going to treat water as a continuous medium with a dielectric constant of some value. Of course, we saw that the dielectric constant in water comes primarily from the rotational alignment of the fixed dipoles in the water molecules. The calculation, however, can also apply to other kinds of solvents. And in fact, what we're going to do is we're going to approximate the core of a protein later on as a continuous medium or pseudo-solvent with a much lower dielectric constant, let's say about 4, that reflects the polarizability of the atoms in the core of the protein, as opposed to the rotation of fixed dipoles that happens in the liquid solvent. Okay, so we start with this uncharged atom, and let's say for the moment it's in water. And what we're going to do is we're going to slowly introduce charge into it. And the idea here is that we take an infinitesimal of charge, right? So this is going to be a calculus-based computational procedure. We're going to take an infinitesimal of charge, and we're going to move it into this previously uncharged sphere that is representing the atom. And so this first step in which charge is introduced will bring the total charge to just dq, or some infinitesimal of charge. And now what we're going to do is a procedure whereby we progressively add additional infinitesimals of charge until we charge this atom up to some final charge value. And so the idea here is by adding progressively charge in infinitesimal steps, we can basically calculate the work involved in bringing in each infinitesimal of charge. And right, this comes back to our definition of work as the path integral of force over distance. We're actually going to use the result we derived earlier for the electrostatic potential, or the work required to bring two charges together at a certain distance. And then we'll use that earlier result derived from this equation to get the enthalpic cost, or the work involved in bringing in each infinitesimal of charge. And then we will do an integration over that charging process that progressively adds infinitesimals of charge. Okay, and so the increment of work involved in introducing each additional infinitesimal charge will be given by Q, the charge on the sphere at a given point in this procedure, times dQ, the infinitesimal charge being brought in any individual step. The work will be Q times dQ over epsilon r. Right, and so Q, again, this is the charge at any point in the chart, at any step in the charging process. If there is currently a charge Q in the sphere, and we bring in an increment of charge dQ, the electrostatic potential energy involved in bringing that charge in is given by Coulomb's law. And so the infinitesimal of work done in bringing that infinitesimal charge in is Q, current charge times dQ, the new charge, over epsilon r. Again, this is simply Coulomb's law. I guess there's some sort of rather sophisticated physics, some principles of electrostatics that are at play here. They're in the background as this is drawn out on the slide, but in brief, you can prove that if you have a charge, a certain amount of a total charge Q distributed over a conducting sphere, that the lowest energy configuration of that charge actually has it distributed with an even density over the entirety of the surface, and the net electrostatic field of that charge the electrostatic field of that charge behaves as if the entirety of the charge were centered at the origin. And so what that means essentially is that a charged sphere, whether the charge is distributed over the surface or whether it is homogeneously distributed throughout the volume of the sphere, either way, the electrostatic field of this spherical charged object behaves as if all of the charge was centered at the origin. And so that means when we bring in an infinitesimal charge to the surface of it, again, there's a theorem that tells you the lowest energy configuration of a group of a number of charges on the surface of the sphere has them evenly distributed essentially over the surface of the sphere. And so that means, effectively bringing in an infinitesimal charge to the surface is equivalent to introducing that charge effectively into the sphere. And so that allows us to calculate very simply, again, the infinitesimal or increment of work done in bringing in an infinitesimal charge into the surface of a sphere that already has charge Q. And that is, again, Coulomb's law, effectively Q dQ over epsilon, the dielectric constant R, divided by the dielectric constant times R. So what we want to do now is to figure the total amount of work involved in charging the sphere from 0 to final value Q. So we simply integrate Q dQ over epsilon R. Of course, this is now an integration over Q, so epsilon R comes out, right? The radius of this atom is fixed during this procedure. It is always R, right? That is the fixed radius of this conducting spherical atom. So that means we can bring the epsilon r effectively out of the integral, and we get the integral of Q dQ. That is, of course, 1/2 Q squared. And so we get the integral is Q squared over 2 epsilon r. If we start uncharged and go to Q final, this reduces very simply to the work done in charging the sphere being Q squared over 2 epsilon r. So this is a very simple mathematical equation now that describes, again, the energy taken to charge up this sphere. Well, what is it telling us qualitatively? It's saying that the work we need to do here goes down as the dielectric constant goes up. It's also, of course, dependent on the radius of the sphere. Small radius, that means basically we're packing the charge into a smaller volume. Therefore, we need more work to get it in. That's sensible. But importantly, higher dielectric constant, epsilon, lower amount of work involved to charge up the sphere. Well, why is that? That's because the dielectric constant reflects, again, the polarizability of the solvent in the electrostatic field, the tendency of the solvent to rearrange its charges to compensate for the electrostatic field. This calculation gives you this calculated charging energy is called the Born self-energy. Self-energy means it's sort of the energy of the charge itself in this medium. Okay, and this, of course, this whole procedure reflects another example of the first law in action. So this is another specific mathematical, physical incarnation of the principle of heat equals work equals enthalpy. This form is the Born self-energy. This form of enthalpy. Right, so now epsilon is 80, as we said earlier, for water. It's about 2 to 8 for apolar solvents. In people who, you can actually model many properties in a protein interior effectively by treating it as a continuous solvent. Obviously, this isn't physically accurate. The interior of a protein has fixed structures in it, but you can treat it as a very low dielectric constant solvent. And what this is saying effectively is that the fixed dipoles in the protein can't really, in the core of it, where it's all packed, they can't easily rotate around. But of course, the atoms in the core of the protein are polarizable. And those polarizable atoms produce in something like, effectively a sea of polarizable. It's like the core of the protein is something like a continuous polarizable medium that can interact with electrostatic charges via the polarization of the electrons in the atoms, but only interact very weakly. So if epsilon is 4, we would get, in the core of the protein, we would get Q squared the total final charge over 2 times 4, or 8R. But if epsilon, on the other hand, if the charge is in water, the absolute dielectric constant is 80, and we would get Q squared over 160 R, or 1/80th the value. And so effectively, charging up this sphere in water, to summarize, takes 80-fold less work than charging it up in a low dielectric constant environment, such as the core of a protein. And so what is the work, what is the work being done here? Well, the work being done here is that of bringing the charge in close proximity sort of to itself. That's why it's called the self-energy. So it's the work involved in getting this much charge into this much volume. So it effectively comes from the repulsive interactions between the charge. Now, why is that attenuated in a high dielectric constant medium? It's attenuated because the solvent species, the water, the dipoles in the water, can orient themselves around this charge in such a way as to compensate for it, interacted with it in a favorable manner electrostatically. So I'll come back to that in a moment, but before we explain that in a bit more detail, let's think about the consequences of moving a charged atom or species from a high dielectric constant environment to a low dielectric constant environment. And this is really what the Born self-energy calculation is useful for. This is widely used by ion channel biophysicists and electrophysiologists because the ion channels effectively allow ions, charged particles, to diffuse through membranes. Obviously, this is a tremendously important process physiologically in terms of neuroscience. The particles penetrating through charged particles penetrating through a membrane is a low probability event because, of course, the membrane of the core of the membrane is extremely hydrophobic. That's why the ion channels produce a path through which it's easier for the charged ion to pass through the membrane. And so ion channel physiologists actually use this Born approximation quite extensively in some of their work. But it's useful beyond that. It's useful even in many areas, and it's useful in particular to think about what happens as we'll see in a few minutes, when a receptor-ligand complex forms, or later we'll think about the implications of this when a protein folds. When a protein folds, a charged group on the protein, if it's may end up going from effectively exposure to the solvent, right? It might start when the protein is unfolded, all of the groups are exposed to the solvent. If the charged group is in the core of the protein, it will effectively involve moving the charged group from this high dielectric constant solvent environment to the low dielectric constant of the protein interior. And so the Born approximation gives us again, an approximate quantification of how much energy it takes to do that. So let's go just apply the calculation. So the idea here is we would slowly remove infinitesimal amounts of charge. Again, this is another Gedanken experiment, as it's called. We remove an infinitesimal amount of charge from the charged sphere in the aqueous environment, and then we bring it very, very far away in the aqueous solution, and then we bring that infinitesimal amount of charge into a sphere in the low dielectric constant environment. And so we progressively, in infinitesimal increments, decharge, as it were, the sphere in the aqueous environment and charge up the sphere in the apolar environment. So this process is going to be exactly, the Born charging process. And this process will be the energy involved, the work involved in charging this up will be given exactly by the Born self-energy that we calculated in the last slide. And basically, based the fact that to every action effectively there's an equal and opposite reaction, the law of conservation of energy essentially means that the energy gain involved in decharging or removing charge from this charged sphere has to exactly equal the work that we would have done actually to charge it up in the first place. So in other words, we can use the Born calculation to also calculate how much energy we gain back when we decharge this sphere. And so then if we use the Born calculation right, so the process then is, right, that's what this is supposed to illustrate. We start with all of the charge over here in the sphere in the aqueous environment. We move infinitesimal increments of charge from that sphere to the sphere in the apolar environment. Eventually, we end up with no charge in the aqueous environment, all of the charge transferred to the apolar environment. The net energy, or the net amount of work involved in doing that, is simply given by the Born self-energy we end up with over here, Q squared final over 2 epsilon protein R, minus the amount of work we would have, basically the work that was, the energy that was gained. The reverse of the work done charging up the sphere in the aqueous environment is basically the energy that is released or gained when we decharge or remove charge from the sphere in that environment. So again, that's just exactly the inverse of the Born charging process, and therefore the energy released by that has to be exactly the negative of the work that was done in charging the sphere up. So we have basically done an amount of work equal to Q squared final over 2 epsilon protein R, and we have released an amount of energy from the decharging process equal to negative Q squared final over 2 epsilon water R. So Q squared final is the same, 2 and R are obviously the same, and so what that means is the net work done in this charge transfer process is 1 over epsilon protein minus 1 over epsilon water times Q squared final over 2R. And so again, epsilon, the interior of a protein, can be approximated as a continuous medium with a low dielectric constant of 4, whereas the water has a constant of about 80. So this ends up being 1 over 4 minus 1 over 80, or about 0.2375 times Q squared final over 2R, R again being the radius of the charged particle. So what this says is that we need to do, in this case, so Q squared, that's obviously a positive value. R's radius is a positive value. So this is a positive value. This quantity is greater than 0. We had to do work in moving the charge from the high dielectric constant environment to the low dielectric constant environment. And this very simple calculation gives us a reasonable estimate of the amount of work done. And so what is going on here physically? Well, the key point is that in the aqueous environment, in water, the fixed dipoles on the water atoms will rotationally reorient themselves so that they interact in a favorable electrostatic manner with the charged particle. And so if the particle has a negative charge, the positive end of the water dipoles will tend to align itself towards the negative charge on the particle, and you will gain a favorable electrostatic interaction between the water dipoles and the particle. And that basically is so essentially you will release heat, you will gain energy, you will go to a low potential energy state. It is energetically favorable to have the water interacting, solvating the charged particle. And so charged particles have strong solvation enthalpy. And basically, to move the charged particle out of the water into the low dielectric constant environment, you have to desolvate it. So the Born calculation basically is a way of calculating solvation and, importantly, desolvation energy. When we go from a very polar solvent that has fixed charges that can reorient themselves and make strong electrostatic interactions, we have a very high solvation energy.
It's
so
10:30.
This configuration gives a low potential energy. It is energetically favorable. To desolvate it, right, to move the charged particle out of this environment, we need to desolvate it. We need to break these favorable electrostatic interactions. And that will be energetically costly, and we will have to do work to do that. When we bring it into low dielectric constant environment, we'll get some energy released because this environment is polarizable to an extent. You will get effectively van der Waals interactions between the polarizable atoms that make up this medium and the charged particle. That will, again, release some energy. You will get some favorable low electrostatic potential energy. But if this is a only slightly polarizable medium, you will only recover a little bit of enthalpy due to the solvation over here, whereas you will have a very high enthalpy loss when you rip apart the much stronger solvation over here. And again, the Born self-energy calculation gives you a way to approximate the amount of energy involved. And this turns out to be reasonably accurate, reasonably informative description, reasonably quantitatively. It's not reliable out to the decimal place, but it gives you good, let's say, better than order of magnitude estimates of how much energy is involved in processes of this kind. It conceptually is tremendously useful because it sort of highlights the important kinds of work and the important kinds of electrostatic potential energy interactions that are going on in this process. And again, quantitatively, it's somewhat useful. And it's particularly useful for people who work on ion channel, in ion physiology. Okay, so to summarize all of that, the energetic cost of moving a charge from a high to a low dielectric constant environment reflects stronger electrostatic interaction with the medium with higher epsilon, that should be, or dielectric constant. Therefore, more work must be done in disrupting the electrostatic interactions with the high epsilon medium than is gained by electrostatic interactions with the low epsilon medium, and this is called the solvation effect. So that's the key point. When you're in the high dielectric constant environment, you have strong electrostatic interactions with the solvent. That is, again, referred to as solvation. To move the charge out of that environment, you have to disrupt all these favorable interactions. You do pick up some favorable solvation energy, but in a low dielectric constant medium, there's much less of it. And so there's a net energy. You need to put in energy because the enthalpy, the heat release, the enthalpy gain over here is nowhere near as strong as is nowhere near as high as the amount of work that needs to be done, the amount of heat that needs to be input to disrupt the stronger solvation over here. Okay, so let's think about how this can control. These effects are important in controlling the formation of biological structures and in mediating interactions between receptors and ligands. And so this is a schematized example of, let's say, two protein surfaces that we're going to consider what happens when they interact with one another. So when we have two protein surfaces in water, the charge groups on those surfaces will be strongly solvated. They will have favorable electrostatic interactions with the dipoles in the water. And again, with the high dielectric constant environment, those interactions are quite strong. When the interface forms, the water is going to be squeezed out of that interface. And so that means that all of these favorable electrostatic interactions have to be disrupted effectively in the same way that they had to be disruptive when the ion was removed from water to be transferred into a new environment. Same principle, same kind of desolvation effect. In this configuration, when we have a partially negatively charged carboxyl group interacting with a partially positively charged amide proton, we pick up a favorable electrostatic interaction. If this geometry is optimal, this kind of hydrogen bond can be energetically very favorable, as we've discussed before. And so, although we lose the favorable solvation energy due to the desolvation process, the water being squeezed out of the interface, we recover good electrostatic energy in this configuration. The interface of a protein ends up being, in terms of its physicochemical properties, very much like the core of the protein, and therefore we can approximate the interface of the protein as having a very low dielectric constant, let's say approximately 4. Okay, so to summarize this, interface formation disrupts solvation of partially charged groups on protein surfaces. The hydrogen bonds and salt bridges in the interface, I'm just getting ahead of here a bit. The hydrogen bonds and salt bridges in the interface provide favorable electrostatic interactions that compensate for the enthalpy loss due to desolvation. So you replace good solvation enthalpy with potentially better hydrogen bonding or salt bridging interactions. However, note that without such interactions, the Born effect would create a substantial enthalpic penalty upon interface formation. So let's think about that. The implication here is that H-bonds play a critical role in establishing structural specificity in interfaces and other biochemical structures, such as the DNA double helix. We won't talk about that explicitly, but the same kind of electrostatic physical chemical phenomena are involved. But anyway, although desolvation is enthalpically costly, if you recover good electrostatic interactions, as you do in this configuration, this is enthalpically happy, and in fact you can get a net gain in enthalpy. Although you've lost enthalpy through desolvation, you can have a net gain in enthalpy due to having a sufficiently geometrically optimized hydrogen bond. So now consider what happens instead if we were to bring one of these charge groups into a protein surface where it contacted a hydrophobic group. In this case, you would still have the desolvation effect. The carbonyl group would still have to lose its favorable electrostatic interactions with water in the process of desolvation as the water is squeezed out of the interface. And however, you would not pick up such a favorable electrostatic interaction. You would have effectively some kind of something like a hydrophobic hydration interaction in here. You would have effectively a rather strong van der Waals interaction. The fixed charge in the carbonyl would polarize the electrons in the hydrophobic group. That would be, effectively a strong kind of van der Waals contact. But in practice, these are not enthalpically strong enough. These are not energetically strong enough. The enthalpy gain from this kind of interaction is not sufficient to offset the enthalpy loss from desolvation. So effectively, in this scenario, you lose enthalpy because the small amount of enthalpy you gain from this van der Waals, although this is a strong van der Waals interaction, it is still recovering less enthalpy than you lost from desolvation, stripping all the water molecules off of the partially charged group on the protein surface. So this is an unhappy interaction enthalpically, meaning it is enthalpically costly. Heat work had to be done. Heat had to be put into this system to produce to form the interface. Because work needed to be done to do the desolvation, in relatively little favorable electrostatic potential energy was picked up in the interface itself. Now suppose instead of bringing the carbonyl group into the interface, we bring two hydrophobic groups into the interface. Well, this situation is once again favorable. We'll see in more detail why this is favorable later on when we talk about entropy and we talk about the hydrophobic effect. But basically, the solvation of hydrophobic groups, although it is important, and in the tail end of the slide stack, we'll talk about how, especially at low temperature, solvation of hydrophobic groups is really quite experimentally and phenomenologically significant and biologically significant. But let's say at 37 degrees, the hydration energy of hydrophobic groups is relatively weak. And so in this situation, although hydrophobic groups are still hydrated when they're in solution, they're hydrated much more weakly. Although they still have to be dehydrated or desolvated when they're moved into the interface, there's much lesser energy enthalpy loss in doing this. And something that is not spoken about here explicitly, but that we'll talk about in great detail later in the slide stack, is the entropy involved in the solvation process. To foreshadow that, when water molecules are interacting in an electrostatically favorable manner with something, whether it's via a hydrogen bonding interaction or a van der Waals interaction, the electrostatic interaction, for it to be enthalpically favorable, the water molecule has to be in close proximity and has to maintain some specific geometry, at least transiently, and therefore its motion is restricted. And so solvation is entropically unfavorable for the water, even though it is enthalpically favorable. Effectively, when you bring two hydrophobic groups together at roughly physiological temperature, there is a little bit of a dehydration penalty. You still have to dehydrate. That still costs some enthalpy. You do, of course, gain van der Waals interactions at the interface. Those offset that enthalpy loss at least to some extent. But the release of the water from these constraining interactions actually has a very favorable entropy gain associated with it. We'll talk about that in much more detail later in the slide stack. So again, the two hydrophobic groups in proximity, bringing two hydrophobic groups together in the interface is effectively energetically favorable compared to in bringing two hydrophilic groups, two charged groups together, especially if they make a nice tight hydrogen bonding interaction, is enthalpically favorable. But when you have one hydrophobic group and one charged or partially charged or hydrophilic group, that's problematic because you have to desolvate. You have to disrupt the stronger solvation energy, the stronger hydration energy of the hydrophilic group without gaining really good enthalpic interaction in the hydrophobic interface. And so just to revisit that point, replacing both interaction partners with hydrophobic groups tends to produce only a modest reduction in stability, but polar interactions still play a critical role in determining binding specificity and are prominently represented in protein interfaces and other biochemical structures. So we'll talk about this later in the slide deck, but the bottom line is that the enthalpic gain from a good hydrogen bond is modest, simply because hydrogen bonding groups, when they're exposed to water, they hydrogen bond with the water. They have good hydration enthalpy. The hydration has to be disrupted. You have to do work to strip off the hydrating water molecules. And so that loss of enthalpy, so the input of heat needed to affect the desolvation tends to offset any gain in electrostatic potential energy, any favorable electrostatic potential energy at the interface when these groups are charged. So that hydrogen bonding interface can still be favorable, but it is not anywhere near as favorable as being is in a vacuum, and so in fact it tends to be enthalpically favorable, but only let's say modestly favorable. On the other hand, if the charged group ends up getting nestled up against, as we saw earlier, if the charged group is going into an interface and it is desolvated and you have that enthalpic penalty and you bring it in contact only with a hydrophobic group, which will only have weak van der Waals interactions with it compared to a strong hydrogen bond, that is energetically unfavorable. And therefore the polar groups in the interface, they contribute perhaps only modestly energetically to the formation of the interface. But they still are incredibly important in determining the specificity of the interface formation because basically this is a happy or favorable interaction thermodynamically. This is a much less favorable interaction thermodynamically. And so when the interface forms, the carbonyl group is going to be highly biased towards being in contact with the amide group. And again, that may yield only slight or relatively modest stabilization enthalpy at the interface. But the alternative of having this kind of loss of hydration of the polar group while gaining only a van der Waals interaction, that is energetically much less favorable. And so the specificity of structures in interfaces in receptor-ligand complexes really depends critically on these polar interactions. Okay. Now, in the background here is a phenomenon called enthalpy-entropy compensation. Talk about that extensively towards the end of this course section. But we're beginning to see what that phenomenon is about and see its importance in this set of slides. Effectively, when the water is interacting with the charge groups on the protein, it is motionally constrained. And so you pick up favorable enthalpy in the solvation process of the charge groups, but you lose entropy in the water molecules because they are motionally constrained when they are making those enthalpically favorable interactions. So again, this phenomenon is quite pervasive in solution thermodynamics. It's called enthalpy-entropy compensation. It reflects the fact whenever things are close enough to have a favorable enthalpic interaction, they are motionally constrained. They have to be over here, right? This water to hydrate the carbonyl has to be here. It can't be over here. It also has to be aligned properly. So the motional freedom of the solvent is reduced intrinsically in the process of having an enthalpically favorable solvent-solute interaction. And so that means in general, favorable enthalpy of solvation is associated with unfavorable entropy of solvation or loss in motional freedom of the water. And this is a really fundamental phenomenon in solution thermodynamics because life takes place in aqueous solutions. Life is a water-based phenomenon. This is a tremendously important physicochemical phenomenon in terms of determining the chemical, biochemical, and ultimately physiological properties of living systems.